A computer CPU understands instructions written in machine language, which is generally in binary format. It is pretty difficult to write programs completely in machine language. For example, this string of binary bits is instructing the computer to read contents from the main memory to CPU. It should be obvious by now that we would struggle a lot to write even simplest of the programs if we were to write them in machine language. Hence, computer scientists in early days created what's called an assembly language, where the code was readable and made more sense than staring at string of zeros and ones. These individual instructions that you use to write a program are called statements. To translate a program written in assembly language to machine language, a special program called assembler is used. Now let's talk about the set of instructions a CPU can execute. Every CPU chip comes with a specific instruction set. For instance, Intel's first commercial computer chip has the following primitive instructions. Everything that is processed on this particular computer is executed at the core using just these instructions. You might be wondering how these primitive instructions can execute complex programs that we use in day-to-day life. That is why computer science is fascinating. Every computational task executed by computer follows just these primitive instructions. Let me show you a quick example on how to perform complex computations from a simple instruction. Here is an example of multiplying two numbers. If we do not have a multiplication primitive operation on the chip, what we could do is add one number, 3 in this example, 7 number of times. Adding 3 7 number of times will give you 21, which is basically 3 multiplied by 7. In reality, more efficient techniques exist for performing multiplication by performing bitwise operations. Typically, computers use electronic circuits comprising of binary adders to perform multiplication. Alright, whenever you try to execute a program stored on a disk drive on your computer, it would follow the fetch, decode, and execute cycle. The program is fetched into the main memory, and then the CPU executes the program by following the instructions step by step. There can be lots of back and forth operations between CPU and RAM. If the program generates a lot of data, then there would be a back and forth between RAM and disk drive as well. Assembly language is quite close to machine language and is considered as a low-level language. To make the life of programmers a little better, high-level languages were developed in late 1950s. Modern computer languages you hear often, like Python, Java, C++, are all high-level languages. These languages are close to the human languages, which consist of words and rules like grammar. Formally, a high-level language consists of keywords, operators, and syntax. Keywords are basically reserved for a specific task or functionality. Here are the list of keywords in the Python language. And then they have operators which can perform various operations on data. For example, here is the snapshot of operations in Python language. Now let's talk about syntax. Human languages also have syntax rules. We tend to be a bit lenient on mistakes pertaining to the usage of commas, capitalization, apostrophes, etc. But when you write computer code, you have to strictly follow the syntax of the specific high-level language. The first high-level language you learn shapes your skill of writing code while learning programming principles. For this course, that language is Python. There are few differences in the way the code is translated into machine code in high-level languages. For instance, Java uses a compiler to translate code to machine language. When there are no syntax errors, the compiler creates the machine code, which can be directly executed by the CPU. On the other hand, Python uses an interpreter which not only translates the code but also executes it immediately, statement by statement. This lets us evaluate our code step by step and get a sneak peek of the target output. As the interpreter directly executes the translated code, no machine code is saved separately, like the compilers.